Hello, calculus friends. This is AP Calculus section 5.4 Day 1 notes. Today we're going to start by talking about some of the properties of the definite integral. Now remember, we define a definite integral as an integral that has limits of integration on it. So we are talking specifically about the fact that there's a value here for a and a value here for b for along our integral symbol, those limits of integration, right? And up to this point, we have always assumed that our a value is less than our b value as we go across our graph from left to right. But the definition as a limit of a Riemann sum makes sense even if that's not true, even if our a value is greater than our b value. So notice first that if we were to reverse a and b, then our delta x would change from b minus a over n to a minus b over n. And basically that just makes our integral become negative, right? Instead of going from b to a, we are going from a to b, and it is the opposite of that. And one special circumstance would be if a is equal to b, well then our delta x is equal to 0, and it makes sense that our integral would be equal to 0 because if you're not moving a distance across the x-axis, then there is no area to find. Therefore, the value of the integral would be 0. So I think that that one's fairly intuitive when you think about it from a graphical perspective. We have three properties, comparison properties of the integral that we're going to talk about today. The first one says that if f of x is greater than or equal to 0 for a less than or equal to x, less than or equal to b, then the integral from a to b of f of x dx has to be greater than or equal to 0. So in layman's terms, this just means that if our function is positive above the x-axis, then the integral represents the area under the graph, and the geometric interpretation of property 1 is simply going to be that that area above the x-axis is going to be a positive value. The second property says if the function f of x is greater than or equal to the function g of x, so now we're looking at two functions graphed in the same coordinate plane over an interval a to b, then the integral from a to b of f of x should be greater than or equal to the integral from a to b of g of x. So basically property 2 says that if f of x is a bigger function, it should have a bigger area over a given interval. That also makes good sense. Finally, property 3 says that if we have some value, we'll call it little m, which is less than or equal to the value of our function, and we have some value, we'll call it big M, which is greater than or equal to the value of our function over some interval a to b, then little m times our interval b minus a is less than or equal to the integral from a to b of f of x dx, which is less than or equal to big M times b minus a. Basically, this is illustrated with a picture here, and it says that if we have this function f of x and we call the horizontal line little m the minimum value of the function, and we call the horizontal line capital M the maximum value of the function, then it makes sense that the area of the rectangle above the x-axis but below little m has to be smaller than the area under the function, but the area under the function has to be smaller than the rectangle created by the x-axis and capital M, right? So basically the area of our function has to be somewhere between those two areas. And when you look at that picture there, you can kind of see what we're talking about, and that makes good sense, right? Our first example today, example 1, we're going to be using that third property that we were just talking about to estimate the value of the integral from 0 to 2 of 1 over x squared. And I apologize, this is missing a dx at the end, so we should have a dx right here. And I have a hint here. It says start by looking at the graph of the function. So I know that the integral that I'm looking at, my limits of integration are from 0 to 2. So when I graph this, I know that I'm going to be focusing on 0 to 2 on my x-axis. So I might go from -3 to 3, and from 2 to negative 2 on my y. I'm not sure. Let's take a look at the graph and let's see what this is going to look like. So we grab our graphing calculators, and in y1 we type in our function, which is 1 divided by, and then we need a parenthesis for our denominator, which is 1 plus x squared. And again, if we look at our window, I'm going to make my window on the x-axis from negative 3 to 3. Again, my interval of integration is just 0 to 2 though. And I'll leave my y scale or my x scale at 1, and then I'm going to leave my y's as they are from negative 2 to 2 on the y-axis. So now I go ahead and I take a look at my graph, and it looks kind of like a normal distribution curve or like a bell curve. So I can go back to my paper and I can easily sketch what that looks like. And it looked something like this. Right? It's not a perfect drawing, but it's good enough. And so again, I am looking at the value of this integral from 0 to 2. Well, this was a point on my curve right here. This is the point 0, 1. And I don't know exactly what this point is right here. But if I go back to my graphing calculator, I can have my calculator calculate what that is for me. So if I want to know the value of the function right here when x equals 2, I can just go second level, calculate value, which is number 1. So I hit enter. And then I'm just going to type x equals 2. And my calculator tells me that when x is 2, the value of the function is 0.2, because I do need to know that point. Okay, so going back to my graph here, this point right here is when x is 2, y is 0.2. And again, I am trying to integrate this function, or look at the integral of this function from 0 to 2. So this is the area that I am looking at under the curve. And property 3 says that if we trap the highest value of the function and the lowest value of the function, if we trap it between those two horizontal lines, that we can estimate the value of the integral by looking at the areas of those two rectangles that are created. So in the picture that I have drawn right here, that means that I'm going to draw a horizontal line right here, because this is my maximum value of my function. And so that in this case is my capital M. And the value of the function when x is 0 is 1. So my capital M has a value of 1. And then my lowercase m is going to be right here. So that's where I draw my other line. And my little m is 0.2, that value that we just found. And so basically what we're trying to say with property 3 is that we have a rectangle that is created by our limits of integration from 0 to 2, and by our x-axis and our little m value, and then by our x-axis and our big M value, right? Those create two different rectangles. And basically the property is saying that the area under our curve should be somewhere between the areas of those two rectangles. So let's show the calculus, and then we'll do a written explanation of what we're talking about. In terms of calculus, property 3 says that little m times b minus a is less than or equal to the integral from a to b of f of x dx, which is less than or equal to capital M times b minus a. So if we apply that property 3 to our specific problem here, we would get 0.2 times, and b minus a is going to be 2 minus 0, is less than or equal to the integral from 0 to 2 of 1 over 1 plus x squared dx, which is less than or equal to 1 times 2 minus 0. And if we go ahead and we do the math here, 2 minus 0 is 2. 2 times 0.2 is going to be 0.4. This is the area of the small rectangle. And that has to be less than or equal to the value of my integral from 0 to 2 of 1 over 1 plus x squared dx. But that has to be less than or equal to 2 minus 0 is 2 times 1, which is 2. This is the area of the large rectangle. Okay, so writing out our conclusion in words, we have the area under the curve f of x equals 1 over 1 plus x squared from 0 less than or equal to x less than or equal to 2 is greater than the area of the rectangle with height little m equals 0.2 and less than the area of the rectangle with height big M equals 1. So we know, without even calculating the actual integral, we know that our answer should lie somewhere between 0.4 and 2. So now we're going to change gears a little bit, and we're going to begin talking about the fundamental theorem of calculus. So when calculus was first discovered, it was kind of separated into two pieces, which we've already kind of talked about this year. Those two pieces were the differential calculus part, finding derivatives of functions, which we spent most of first semester on. And then the second branch of calculus was integral calculus, which arose from the area under the curve problem. But Isaac Barrow discovered at some point that these two problems are actually related to each other, and that differentiation and integration are inverse processes of each other. So then together, later, Newton and Leibniz kind of put this discovery together, and they called it the fundamental theorem of calculus. So here in the box, we have our fundamental theorem of calculus, part 1. We'll talk more about part 2 later. But the fundamental theorem of calculus part 1 says that if f is a continuous function on a closed interval ab, then the function g of x, defined by the integral from a to some x value of f of t dt for values of a, or for values of x between a and b, is the antiderivative of f. That is, if we take the derivative of the integral, we just get back the function itself, right? So in Leibniz notation for derivatives, our theorem becomes the derivative with respect to x of the integral from a to x of f of t dt is just equal to f of x, where f is continuous. So again, kind of our layman's terms right here. If we first integrate f, and then we differentiate that result, we get back to our original function f. So our second and final example for today gives us a function g of x, which is defined as the integral from 0 to x of f of t dt, where f is the function whose graph is shown, okay? So part A says evaluate g of x for x equals 0, 1, 2, 3, 4, 5, and 6. So I'm going to tell you right now that you do not have enough room on your paper for part A where part A is located. So you may want to draw an arrow down to someplace below on your paper, perhaps in your summary area, and do the work for part A in your summary space. I apologize for not giving you enough room for this problem. So let's think for a second about what part A is asking us to do. If they want us to evaluate g of x, remember they're asking us to evaluate the integral of the function, or they're asking us to evaluate the area under the curve from 0 to whatever x value they are asking for. So I think the easiest thing to do would just be to start doing it so that you can kind of understand what's going on. So I am going to draw an arrow here for part A, and then I'm going to put my answers down here below. So the first value that I need to find is g of 0. So g of 0 is going to be defined as the integral from, my lower limit of integration is always going to be 0, but then my upper limit of integration is going to be whatever I am plugging in for x. So in this case, 0, right? So the integral from 0 to 0 of f of t dt, well, I'm not going anywhere, right? I haven't crossed any distance. This was that very first property of the definite integral from our notes today. The integral from a to a of f of x dx is 0. Same idea. So we haven't covered any area yet, therefore the value of the integral is 0. Now for g of 1, we are looking at the integral from 0 to 1 of f of t dt. So now we have to look at our graph. And when we look at the integral from 0 to 1, we're looking at that much area. And since this is a nice linear function, we can see that that's a perfect little triangle with a base of 1 and a height of 1. So we know that our area there is going to have to be 1/2. Now, I want to point out to you that as we are moving across our x-axis, the value of our integrals are going to become cumulative, right? So we're always going to be adding on the previous areas. So in this case, it would be the value of the integral from 0 to 0, which was 0, plus the value of the integral from 0 to 1, which we know is 1/2 from our picture. So g of 1 is 1/2. Now finding g of 2, that's going to be the integral from 0 to 2 of f of t dt, which I know is going to be the integral from 0 to 1. I already found that. So 1/2 plus, now I have to add on the part from 1 to 2. So now I have to add this. Well, keep in mind, we just dropped below the x-axis. Any areas that are below the x-axis are considered to be negative areas. So this is going to be plus negative 1/2. So now the value of this integral is 0. G of 3, the integral from 0 to 3 of f of t dt is going to be equal to what we had from 0 to 2, which was 0, plus, now we're adding on another negative 1/2. So now the value of our integral is negative 1/2. Next we look at g of 4, and g of 4 is going to be equal to the integral from 0 to 4 of f of t dt, which is going to be the integral from 0 to 3, which was negative 1/2, plus the area that we get when we go from 3 to 4, which is a positive 1/2, so that takes us back to a value of 0. G of 5, the integral from 0 to 5 of f of t dt is going to be equal to the integral from 0 to 4 plus the area that we gain when we go from 4 to 5, which is 1 and 1/2 positive units. So now the value of our integral is 1 and 1/2. And then finally, g of 6 is going to be equal to the integral from 0 to 6 of f of t dt, which is going to be the value of the integral from 0 to 5, which was 1 1/2, plus new area that we are adding on here, which is another positive 2 1/2 units. So 2 1/2 plus 1 1/2 is going to give us a value of 4. All right, so that takes care of question or letter A, okay? Now, letter B asks us to estimate G of 7, right? Well, we know that G of 7, and again, we're estimating it. Well, it's going to be equal to the integral from 0 to 7 of f of t dt, which we know is going to be approximately equal to G of 6, which we already found, plus the area that we are adding on, right? So how much are we approximately adding on over here from 6 to 7? Well, I could estimate that as being a triangle that has a base of 1 and a height of 3, right? It has a base of 1, it has a height of 3, and it's almost triangular. We know the area is slightly bigger, but this is a good estimate. So I'm going to say 1/2 times my base of 1 times my height of 3. So I'm going to say that it's about an extra 1.5 units that I'm adding on. And remember, G of 6 was 4, so 4 plus 1.5 is going to give us an estimate for G of 7 of 5.5. Okay, that one's not perfect because our function was a little bit curved there at the end. All the rest of our areas were perfect up to this point, but that one is an estimate. Letter C says, where is G increasing and where is G decreasing? Well, keep in mind that we are going to be increasing anywhere where our areas are above the x-axis, and we are going to be decreasing anywhere where our areas are below the x-axis. So I am increasing on the interval from 0 to 1, and I'm increasing on the interval from 3 to 7. I am decreasing where my areas are below the axis on the interval from 1 to 3. Where does G have a maximum value and where does G have a minimum value? Well, it's going to have its maximum value at the spot or at the location where our cumulative area is the greatest. So when we look at our G values that we found, our area is the greatest when x is 7, right? So our max value is going to be at t equals 7. Sorry, I'm saying x instead of t. The axis is technically the t-axis here. And our minimum value would be the point at which we had the smallest value for our area. And if we look at our G values once again, we had the smallest area at G of 3 when our area was actually negative 1/2. So our minimum value is at t equals 3. Okay, now finally, part E asks us to sketch a rough graph of G. All right, so what I am going to do that, I'm going to have to do some erasing of some work that I have down here. So hopefully you already have this recorded so that I can create a little bit more space for myself. And so what I want you to be thinking about as you're making this graph is that the y values of f of t are slopes of g of t. Okay, so we are going to draw a slope field, which we have done before, but it's been a while. Okay, so we're going to draw a slope field. So I'm going to make a little table right now of those slopes. And so my x values here were 0, 1, 2, 3, 4, 5, 6, and 7. Okay. And again, when I am looking at the y values on my graph, on the given graph, these again are going to be my slopes, right? Well, when x is 0, the y value of my graph is right here. I'm putting, let me switch colors. My y value is right here at 1, right? Also hard to read. Here we go. And when x is 1, my y value is 0. When x is 2, my y value is -1. When x is 3, my y value is 0. When x is 4, my y value is 1. When x is 5, my y value is 2. When x is 6, my y value is 3. And when x is 7, my y value is back to 0. Okay? So we're going to create this slope field based on the y values of our function. Okay? And then the second thing that we are going to do after we create this slope field is then we're going to use those g of x values from part A, because those are values of our integral function, right? So we are going to plot g of x values from part A. All right, so I am going to make my graph of g, which is the integral of f, right below my graph of the function here that I was given. So I will put my axis right here. So 1, 2, 3, 4, 5, 6, and 7. Okay, and so the first thing that I'm going to do is I am going to draw in that slope field. So when x is 0, I'm going to sketch a vertical line of line segments that have a slope of approximately 1. And again, this isn't perfect, it's just do your best, okay? And then when x is 1, my slopes are 0, so horizontal. When x is 2, my slopes are -1. When x is 3, my slopes are 0. When x is 4, my slopes are 1. When x is 5, my slopes are 2, so steeper. When x is 3 or 6, my slopes are 3, so steeper yet. And then finally, when x is 7, my slopes are back to 0. Okay, so now I have a lovely slope field drawn. So then my next step is to plot my g of x values that I found in part A. So g of 0 was 0, so 0, 0. G of 1 was 1/2. G of 2 was 0. G of 3 was -1/2. G of 4 was 0. G of 5 was 1 1/2. G of 6 was 4. And we approximated G of 7 to be about 5.5. So right there. Okay, so now the last step in drawing my sketch or my rough sketch of G is just to connect these points while following my little horizontal segments of my slope field. There we go. So there is a rough graph of our function g, which is the integral of our function f.